flow. As we are all aware, whether it is liquid flow, gas flow, or whenever a dip is inserted in a patient, what should be the flow rate at that time? All these are very important measurement, not only for transaction, but for the protection of human life. We have with us Professor P.K. Suresh, who is the retired Deputy Director from Fluid Control Research Institute, Palakkad. And I know very well since last more than about 20 years, I am knowing him. He is one of the key person in our country who knows this flow measurement. We do not have, I think that a person who is having this was more than 37 of years of experience in the flow measurement only. He is actually instrumental for taking this FCRI at the international level. And I know he is a graduate, postgraduate, and all technical knowledge he has. Because if I will say what are the technical knowledge he has, I will be just showing a lamp to the sun. Knowledge, understanding, and the technical know-how, I do not know anybody in our country who can beat him, who can just have an understanding better than him. So sir, really I'm thankful to you. You have accepted our request for delivering a talk on this very important topic. We are thankful to you, sir. We have with us our Honorable Shri B.N. Dikshit Sahab, Director Legal Metrology. Sir, would you like to speak 2 words? Shri B.N. Dikshit Sahab, our Honorable Director, former Director Legal Metrology, Shri B.N. Dikshit Sahab.
Yes, 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 yes.
Please, sir. We have, sir, as you know, we have already discussed about Mr. Suresh, and we are all aware to each other. We are knowing each other very well. And now, sir, as India has already started in this new arena of OML issuing authority, how we can take other laboratories working in our country for this issuing as a for the testing laboratory to become in OML area, so that these testing facilities available in our country can be utilized in a better way, and we can also provide not only these services to our manufacturers but also to the neighboring countries or many other countries who want to get tested and approved their equipments, ring and measuring instruments, and as per OML recommendations, we can think of it. Dikshit sir, please.
So first of all, the congratulations for getting YMLCA certificate. This is a continuous process. A lot of instruments are there, for which we can apply time to time and may get the certifications, and we may enhance the capacity of our RSLs and others laboratories. The topic of flow meter is very important topic. FCRI was one of the key was playing the very key roles in the establishment of flow meters and water meter and so many other testing facility at the RRSS. Now the Mr. P. Suresh, who is the ex-deputy directors, and he's having the lot of experience in the flow meters. I hope that we will get the lot of knowledge from his lectures, and other participants will also get the knowledge, and I hope that he should be the part of our teams, regular teams, and so that we may be benefited time to time. Thank you, Astusi. I hope that this program will be very successful.
Thank you very much, sir. Now I would like to request again our Professor P.K. Suresh sir to kindly take over and let us enlighten us from his invaluable knowledge. Thank you, sir. Please.
Thank you, sir. Thank you for your nice words and introduction. I will try my level best. See, I'm retired, so my memory and other things are slightly faded, it seems. So anyway, I will try to share my knowledge, whatever is there. Let me first congratulate Vaishyan Messrs to obtaining that OEML approval for testing. It will be a big boost to probably Make in India program. because the manufacturers were trying to get OIML approved certificate from various other countries, and it has a lot of problems. They were facing a lot of problems, as we personally know. And now, since you can apply, you can issue the certificate, that will be a great boost to our country. Once again, congratulations to you for obtaining that. You and Dikshit Sab, who were instrumental in applying and getting the certification from OIML.
Thank you, sir. Thank you very much. Thank you, sir.
So now coming back to my subject of the metrology of flow measurement. The metrology as such is a very important aspect of our life. As you take Chandrayaan-3, earlier there was a problem with our rocket or satellites. Satellites, the booster rockets needs your fuel, and the quantity of fuel which is going into the booster rocket will decide the payload which can be loaded to the satellite. So it is very critical that you know the payload is very important in their case, and the measurement of fuel was very important. So I remember long back then we have made a system for measuring isopropyl alcohol for VSSC Trivandrum and ISRO Bangalore for fine-tuning their system for filling fuel into satellites. The satellite needs booster rockets, rocket needs fuel. The fuel has to be measured accurately so that the extra payload can be used for other instruments. So these kind of accuracies and these kind of since then there is a lot of development or advancement in the flow measurement technology and flow measuring instruments. We have developed many flow meters which are much more accurate than those flow meters which are used probably 10 or 12 years back, and now we are using flow meters which are very accurate, which can go up to 0.5% accuracy. When you state that the flow meters which are there which can go up to 0.05% accuracy, people like Agarwal sub, how will they verify that this can go up to 0.5%, whether it is showing something wrong or whether it is showing the claimed 0.05% or so there has to be a verification system. Also, there has to be a calibration system which can ensure that this is 0.05. When you need a system to measure a 0.5% accuracy flow meter, then you will need a system which can measure better than that. Otherwise, the meter will be as good as the calibration system. That is the problem. So developing flow metering and developing calibration system for better accuracy in hand. I mean, it's not mutually exclusive. These two things are to go hand in hand. All the technologies for higher accuracy measurement and higher accuracy verification of the measurement has to be developed. So I would say FCRI was instrumental in developing gradually the flow measurement system in our country. So we were in when we were working, even now they are working on constantly improving the measurement system so that you can calibrate or verify meters which are providing you better accuracy. So earlier, in the beginning, FCRI accuracy was of the order of 0.25% or 0.2%. Now it has come down to 0.05% or 0.03% in certain cases, wherein you can verify the flow meters of 0.5% or even better for smaller flow rates. So this is not only in rocket technology, this is in our day-to-day life also we are facing flow measurement problems. See, if you take the flow measurement problem or flow problem, basically heart attack itself is a flow problem, you know. There is not enough flow into your required vessels, and then you have some blockages and all those things. The block or whatever you call, doctors say block, but we would say a flow measurement, a flow restriction in some of the vessels can lead to critical issues of your health. So health is another area where you have flow measurement is very critical. Pharmaceutical industries, in pharmaceutical industries, it is very critical. In oil and gas, as you know, it is direct money. You are measuring money. So that is very, very important for our country as such. The exploration, while exploring oil or while taking out oil from private parties are taking out oil from exploring the oil, then the measurement and the tax associated, petroleum revenue tax associated with it for the ministry or for the government is very important. All these things, wherever you look into, there is a flow measurement problem. So now let us go to my slides. So measurement, actually what is measurement? Measurement is using some equipment to measure the particular parameter, right? Measurement usually involves using, and this is a definition, usually involves using an instrument as a physical means of determining the property or characteristics of an object or a system. Maybe it is temperature, maybe it is pressure, maybe it is length, maybe it is mass, or maybe it is volume, or whatever it is. You use an instrument for determining that property or that particular value, and then use it for your analytics. The instrument serves as an extension of human faculties. It's not the instrument just that, okay, AI, artificial intelligence and all those things are coming, but still you need instrument human brain to fine tune all these things or analyze these things, and then ultimately arrive at a decision from the inputs of the human. So it's technology advances, but the technology advances, there's a demand for more and more accurate instruments also. If the technology advances, the technology advance has to be measured. Anything which is not measurable is not improvable. That is what the saying goes, as that if you cannot measure it, you cannot improve it, whatever it is. If it is, even if it is an administrative problem, you measure it and then improve it. Without measuring, you cannot improve it. When you make a measurement, the measurement has to be accurate. So how do you determine the accuracy of the measurement is also a problem. So the reliability of the data which you collect from various sources, say for example, census data which you collect from various sources and accumulate it, and then how you analyze it, what data you will look for, what is the problem, where to look for the data, what is the data which you are getting, how to analyze it. All these things are important, whether it is a measurement of an administrative problem or a scientific problem or a day-to-day problem. Fluid flow measurement is different from other kind of measurement, because fluid flow, you are trying to measure something which is moving. The other parameters like a meter or a mass of a particular item is being measured when it is static, but the fluid you are measuring when it is moving. The measurement of smoothly moving particles which conform to the piping in an uninterrupted stream to determine the amount of flowing. These things the flow is a bit complicated, I would say. The flow doesn't have a proper characteristics. Without a proper characteristics, or without characterizing the flow properly, you cannot measure it properly. So we assume certain things when you are making flow measurements. One is, it is relatively steady state mass flow. That is, the fluid is steadily flowing without fluctuations. The flow is, when you say the flow is 30 meter cube per hour, the flow remains 30 meter cube per hour, plus or minus something is also there. But it's not varying from 30 to 0 and then 0 to 30 and 30 to, the flow meter will not be able to cope up with such kind of variations. So we are assuming that when a flow meter measures the fluid, the flow is steady mass flow. The fluid is clean, because many of the flow meters, as we would say, the clearances are very low, or the tube size is very small, or you can say the pressure loss becomes more if it is not clean. All these things are problematic for an actual real flow measurement, accurate flow measurement. Then the flow is homogeneous. Heterogeneous flow, it is very difficult to measure. The flow is you are talking about fluid which are Newtonian. Newtonian fluid means the fluid remains, fluid remains, viscosity remains constant even when the flow velocity is increased or the flow stress is increased. Or you can say rather, the fluid takes the shape of the vessel which it contains. Such fluids are called Newtonian fluids. Non-Newtonian fluids are not like that. When you apply pressure, it changes shape. So we are assuming that we are measuring Newtonian fluids. Excuse me. Then we are assuming that single phase, the flow is single phase. Single phase means if it is liquid, it is purely liquid. If it is gas, it is purely gas. The gas and liquid is not combined, or you would say sometimes gas comes, sometimes liquid comes. So you can see the effect of gas coming through a liquid flow meter when you open, when your water is stopped in your home and then it starts coming, the air starts coming and the water meter runs mad, and you pay for the air, not for the water. So it is not good for measuring instrument also, because all measuring instruments are designed for certain velocities. So air velocity is always high. So if you try to pass air through the water meter, then it becomes it can get damaged. Vice versa is also true. Like gas meter, the water enters, or you can say liquid particle enters the gas, then it can damage the meter as well as the measurement accuracy will go. Then another thing is non-swirling profile. Though we assume that the flow which is coming is properly treated, and it is not rotating. Swirling means it is the rotation, the velocity is rotating, like you can say, how would you say, a disturbed flow with rotation. So that is also not good for the flow measurement accuracy. So when you are making flow measurement, you are assuming that it is a steady state mass flow, the fluids are clean, fluids are homogeneous, you are making the flow measurement on Newtonian fluids, the flow is single phase and it's non-swirling profile. So these are the assumptions which you make when you are making fluid flow measurements. Agarwal sir, if there is some questions, then how would I address it? I mean, in between or finally?
Sir, as per your convenience, if you look after on the screen and you find any question which can be replied immediately, it is up to you, sir.
Okay, sir. Okay.
Thank you very much. Otherwise,
Because interactive sessions are better. I mean, I just giving lecture and then people listening without.
no. Yeah, communication, two-side communication is always very good.
Yeah, if I can answer, I will try to answer now. Otherwise, I will come back to you and give an answer later also. That is because I don't remember everything now. So I need some reference. So I will try to answer whatever is possible. I mean,
Please. Please.
so the history of flow measurement goes some 4,000 years back. It's not new. People have been doing allocation measuring. Orifice Orifice is something like a differential pressure flow measuring instrument device that is discovered in 1600. These hydraulic equations, Bernoulli hydraulic equations came in 1700. The Pitot tube came in 1730. Rotary meters came in 1900. So the flow measurement topic is not new, but history is there, but still flow measurement is under constant improvement. So one of the things which weights and measures is involved is the custody transfer operations in flow measurement. Custody transfer occur at various points, so maybe from an oil production platform to a ship or to a barge or rail car, from truck to refinery, from refinery after refining it at various destination points, transportation through pipeline. All these things come in the custody transfer. And I think all these custody transfer applications, weights and measures are involved as far as they could cope with the pressure. So the problem with weights and measures is also that they are also lacking manpower, and everywhere they are not able to pay attention. That's what I felt at that time, and I think it is still the problem is there. So there are so many areas in which the weights and measures can be actively involved, which is needed also, but it's not that easy for them to do all these things with the available manpower. Then the process measurement comes. The process measurement occurs within refineries. The process plants, like the power plant, you take the case of a power plant, you want to know the boiler feed water which is going into the boiler drum, which is very important or critical for the operation of the boiler. So you need a flow measurement of water which is going into the boiler drum. It is not that critical as we see in the custody transfer applications, but it is still critical from the operational point of view. So the process measurement is different from custody transfer measurement. There are many occasions within a refinery or process plant where liquids need to be measured so that the right products will be produced, because some mixing or something can take place. All these things, flow rate has to be maintained, or maybe the process safety aspects, the flow rate has to be maintained. It cannot go above a flow rate. So these kind of aspects is process measurement. These applications can be grouped under title process measurement. So you have two kinds of measurement: custody transfer. Custody transfer measurement is basically money measurement, and so that is why people are more bothered. Process measurement is also equally important from the process, from the point of view of process accuracy of the process and accuracy, quality of the product, all those things. Then I'll go through some tips. Accuracy is the closeness with which an instrument is approaches the true value of the variable being measured. Here the problem is, what is the true value? The true value has to be kept by somebody. So the RRSL does the job for the keeping the true value for you in various parts of the country. So the true value, they have the true value. They compare with the closeness with which your instrument works with the true value. Again, the problem is, if you have an instrument which is more accurate than the RRSL instrument, then it will be difficult for you to claim more than the accuracy which RRSL has. So, or FCRA has. If FCRA has a flow measuring system which is 0.25% accuracy, then somebody with the 0.05% cannot claim that 0.5% until and unless FCRA has the capability, or RRSL has the capability to verify. So that is why it is required that closely monitor the measurement systems and closely upgrade the watch and upgrade the measurement system wherever it is available. So maybe you have to spend for a lot of money for buying equipments or purchase equipments for accuracy, but that is worth doing it, because the closeness of accuracy is very important for every process and for every industry. So that the money spent on accuracy maintenance or accuracy improvement is worth doing it. The precision. Now, you will always say the precision, a measure of reproducibility of the measurement, that is given a fixed value of variable. Precision indicates the degree to which the successive measurement differ from each other. That is, if you make the measurement of a particular value or a particular temperature 2 times using an instrument, it gives 2 different readings which are totally different. Then what is the reliability of that measurement? So the precision or the reproducibility of the measurement using the instrument is very important. The precision is very important for any instrument. Sensitivity, the ratio of output signal to response, resolution, the smallest division which you can measure, the error, deviation from the true value, all these things are part of measurement language, which probably everybody knows. So this probably you would have seen also this particular slide. I don't know, but again I will show you. There is repeatability does not necessarily mean accuracy, but poor repeatability definitely means poor accuracy. So you are trying to you aim at the apple, but you are doing it all over the place. The arrows are all over the place, not at the apple. So it is poor repeatability, definitely poor accuracy also. This is good accuracy. good accuracy and good repeatability. So good accuracy means good repeatability, definitely. But good repeatability not necessarily mean good accuracy. So it's always the wrong reading. It shows always the wrong reading, but you are getting good repeatability, but it is not accurate. So repeatability, poor repeatability is definitely poor accuracy. Good accuracy is always produces good repeatability. Good repeatability does not necessarily mean good accuracy. It can sometimes not accurate also. So what is the Mr. Sharavan Kumar has raised the hand. Can I answer his question? I mean,
Sir,
yes, sir. Mr. Sharavan Kumar has raised the hand. So I think there is a question. Seema Ranjan has also raised the hand.
Can you put your question in the chat box? Kindly put your question in the chat box. Sir, you please continue. As soon as the question will come in the question box or the chat box,
Okay.
we'll take it.
Okay. So the desired limit of accuracy is 100%. So you always need 100% accuracy. But how is it possible? Especially in case of everywhere, the accuracy you cannot aim. You can aim for 100% accurate readings, but it is never 100% accurate. There is some uncertainty associated with every measurement. So flow measurement, as you say, flow measurement is money in many cases, and measurement becomes more complex when two or more parties are involved in the measurement. So the parties never agree with each other's measurement. Sometimes people say you have a meter, one party has a meter, another party has another check meter in line. You have two readings and you have a controversy. Sometimes they put a third meter also and you have pandemonium. These three meters never agree with each other. So everybody will say my meter is accurate. So the verification of the meter with a common system will solve the problem probably. So the measurement becomes more complex when two or more parties are involved. So the measurement decides your bottom line, as you know. It is more than buying a meter. The fluid flow measurement is affected by the fluids. It is affected by the flow. It is affected by the meter. It is affected by the meter calibration also. The fluid means the fluids, as you say, the fluids, what are the kind of fluids which are being measured? So what are the types of fluid impurities which are associated with the fluid? What are the phases of the fluid? And the flow, steady flow. If it is not steady, then you are going to get affected. So the fluids affect the flow measurement accuracy. The flow affects the flow measurement accuracy. The meter affects the meter accuracy, or the meter characteristics affects the flow meter accuracy. As you say, the meter. See, you don't need a most accurate meter for all measurements. It depends on your measurement accuracy requirement. Sometimes you need only a DP meter. Sometimes you need only a vortex meter. Sometimes you may have to go for mass flow meter, where the cost of the fluid involved or the cost of the process involved in the measurement decides the meter. So the meter has to be, because the meters are costly. Say if you take an orifice plate, it is a plate with a hole, and you have a DP transmitter, then you can measure the fluid flow. But that probably cost you less than 10,000 rupees. But if you go for a mass flow meter of the same size, it will cost you lakhs. So it depends on the manufacturer. So whether you need to go for the highest accurate meter for that particular application is your choice. Or your industry's choice, whether it is worth doing that. And the fluids when it comes, say, for example, if you're exploring fluid from exploration, the fluid comes out in three phases. Like it comes in gases, it comes as liquid, it comes as oil. So the fluids has to be treated, or the fluids has to be separated. You have oil separators in exploration field. So the fluids has to be separated to make the measurement. So when you make a measurement, you have to ensure the fluid quality. You have to ensure the flow quality, because most of the flow meters, I would say most of the flow meters depends on the velocity. It is a measure of the velocity of the flow which decides the flow rate measurement. So therefore, if you are measuring in a condition in which the flow velocity is affected by something, then you get an inaccurate measurement. Then the meter, of course, and the meter calibration. So the meter is as good as its calibration. So meter, otherwise it is only a metal piece. So if you don't calibrate it properly, then every instrument is a metal piece. It's not. I won't say you can believe or you can rely on the reading of the instrument until and unless it is calibrated properly with a proper system, with a proper instrument. So the meter calibration is all the more important. So the measurement, the fluid flow measurement accuracy depends on the fluid, the flow meter, the flow, and the calibration. So these are the major four concerns when you are making a fluid flow measurement. Then now, if you ask me what is calibration, or you always say calibration. What is the calibration? A set of operations that establishes under the specified conditions the relationship between values of quantities indicated by device under calibration for a known measured input and that of primary or secondary standard. So it's a long definition, but I would say you have a reliable standard with which you compare the meter under same conditions. Like if you take the case of a flow meter, you do the calibration of the flow meter for various flow rates. Like the accuracy of the flow meter is also affected by the flow rate which it passes through it. So at a very, very low flow rate, the accuracy of the flow meter may be bad. So at a medium operating flow rate, the accuracy of the flow meter is good. If you got a very high flow rate, also the accuracy could get affected. So therefore, under this set of, say, if you are, for example, you have a flow meter which needs to measure flow rate varying from 40 to say 70 meter cube per hour, and you fix up a meter. You do the calibration of the meter from say 10 meter cube per hour to 100 meter cube per hour, but your operating flow range is something like 40 or 50 meter cube per hour. Then while doing the calibration itself, you can adjust it in such a way that the flow meter gives its maximum performance at the operating flow rate. So there is a habit of the people to calibrate the flow meter with the same accuracy from 10 to say 100 meter cube, which is not possible because the flow meter characteristics does not allow you to do that. So where is your interest? 24 hours you are operating. Out of 24 hours, 23 and a half hours, if you are operating the flow meter at 50 meter cube per hour, then your major interest is at 50 meter cube per hour. So you need to obtain the minimum error or the maximum accuracy at that particular flow rate. So while doing the calibration, then you have to ensure that you are getting maximum accuracy at your operating flow rate. If you are concentrating on flow rates which are not in your operable area, that is not correct actually, because you compromise on the accuracy of the flow meter at the operating flow rate to attain accuracy at a flow rate in which you are not operating. So the flow rate at which you are getting the calibrated instrument calibrated and the flow rate at which you concentrate on getting minimum error is also important during calibration. It is important that the accuracy of the reference standard should be preferably 10 times or at least 3 times that of the device under calibration. 10 times is not very practical in case of flow measurement. or any measurement. So you try to achieve at least 2 to 3 times better than the instrument under calibration. Now, there is a concept called traceability. What is traceability? The concept of establishing a valid calibration of a measurement by step-by-step comparison with better standards up to an accepted national or international level is called traceability. The ability to relate individual measurements results to national standards or nationally accepted measurement system through an unbroken chain of comparisons. Unbroken chain of comparison is very important. Unbroken chain means then your all calibrations are valid. Like I'll come to that unbroken chain later. The concept of establishing a valid calibration of the measurement by step-by-step comparison with better standards. Traceability begins with national or international intrinsic standard of measurement and ending with the working standards of measurement of a given metrology laboratory. So that is the traceability chain. Traceability starts with the international standard. It comes to national standard. In our case, National Physical Laboratory (NPL). Then it goes to working standards. Then it goes to measuring instruments. Probably you can say in our case NPL, RRSL, or laboratories like FCRI, and then you can say working standards of other industries, and then from there working standard to the measurement instrument. It's not possible to calibrate every instrument to the national standard by the national standard or RRSL. So we have a concept of transferring the standard from RRSL to other measuring instruments, which will give you a reasonable accuracy for your measurement system. I won't say the best accuracy, but reasonable accuracy, which is you don't have to aim for more than that, which is not practical also to calibrate every instrument at RRSL or NPL. So traceable measurements are essential for interchangeability, for support of international trade and commerce, for ensuring uniformity of goods and industrial process. All these things are basic theories where you need the traceability, because 1 kilogram measured here and 1 kilogram measured in America cannot change. So it has to be same. So flow meter accuracy, like the flow meter accuracies, some American flow meters which calibrate their flow meters in their system with 0.1% accuracy in volume. When it comes to India, it cannot change to 0.5% because we are also aiming at 0.1%. We believe that their standard is same as ours. Yeah, there is a question that any tolerance is allowed in the measurement. Yeah, tolerance is allowed as per OIML flow measurement, OILR 117. You have different classes of measurements. Tolerances are specified in OIML R117. OIML R117 is freely accessible from OIML site. You can download it and then look for tolerances for various kinds of fluids or various kinds of measurements it is given. It ranges from, if I remember, it ranges from 0.2% to some 2% or something, or 1.5%, something like that, for various kind of measurements. So tolerance is allowed. Tolerance is allowed and tolerance is required also. You cannot operate a system without tolerance. So nobody is perfect. No instrument is perfect and no people are perfect. So all these things affect your measurement. Therefore, tolerance is allowed and tolerance is there. So when you start from national standard, you have a transfer standard. National standard itself will have a transfer standard. Then you have a working standard. Then your measuring equipment. Working standard is probably kept by RRSL. So national standard is kept by NPL, and they have the duty to maintain the national standard by rule. They have the authority and duty to maintain the national standard. They transfer the standard to other. So as you can see, the pyramid goes from national standard or international standard at the pinnacle, and then it goes to the national standard, to transfer standard, to working standard, to measuring equipment. As you go away from the national standard, the width of the pyramid signifies the measurement uncertainty, or the uncertainty with which I think you are familiar with the term uncertainty. Uncertainty is the lack of certainty. So uncertainty, how when you make a measurement, you would say it is 5 mm. You are certain that it is 5 mm within a limit of say 5 mm plus or minus 0.001 mm. So that is the uncertainty associated with that measurement. That bandwidth, that is the uncertainty bandwidth, will go slightly bigger when you go to the bottom of the pyramid. So at the pinnacle, you have national standard. When you make measurements using other standards and then go away from the pinnacle, then your measurement uncertainty also increases. The calibration hierarchy indicates that, but the increase in hierarchy, increase in uncertainty will depend on the transfer standard uncertainty and the conditions under which they're being calibrated. You cannot say that it is very bad. It is there, always there. Worldwide, the uncertainty is there. Calibration hierarchy is there. Calibration uncertainty increasing while it goes down the pyramid is also there. It's a common phenomena which happens everywhere, every country. So it's not new to our country. Everywhere it is there. Now there are always question asking about how the methods are adopted for fixing calibration interval. This is actually legal metrology. As legally, I think it's a legal metrology, as per legal metrology's rules, it is 1 year. Please correct me if it is I'm wrong, sir. It is 1 year, but as far as you are concerned, you can say, for example, if you are using a standard for calibration, like a flow meter, which is used as a master meter for calibration, which is very rarely used, then you can use that master meter calibration, say once in 2 years or once in 3 years. But depending on the accuracy criticality, you may go in for once in 6 months also, because even for 6 months you are not able to sustain if there is a loss. Suppose I will tell you an example. Suppose you have a flow meter which measures say 50 tons of naphtha per day. The naphtha cost is something like 70,000 per ton per day. So if you have 1% inaccuracy, you imagine what is the loss you are going to incur. Your flow meter is showing minus 1% in your measurement. Minus 1% is how much? If you are measuring 20 tons of naphtha, minus 1% is 2 tons. 0.2 tons per day. So take 30 days, it is 15 tons per month. 15 tons into 70,000 rupees, which is too high. You take it for a year. So the amount of inaccuracy you can, you can accommodate will basically depend on the calibration interval. So manufacturers specify so many things. Certain manufacturers say that it has never to be recalibrated. It itself, the meter itself takes care of the calibration based on the certain readings. I humbly disagree with that kind of specifications, because you need calibration for the instrument. It's not because I used to work for FCRA and FCRA makes its income out of calibration. It is because the instrument can misbehave sometimes due to various reasons which are not defined or which are not known to us. So therefore, it has to be verified. There has to be some means to verify the flow meter once in a while. So at least once in a year. Then you have control chart method. Depending on the flow meter's performance, you make the inaccuracy chart and then find out at what interval it goes out of behavior. That is one method. Model number method, data pertaining to a particular model is available with you, then you can decide based on the model number. usage time, for how much time you are using it. Maybe you, if you are using once in a year or something, then you can do the calibration or verification once in 3 years or so. In-service testing method. Then in-service, if you have a verification method, you can do that. So all these things are to be decided by the user. I am saying this apart from the law. If the law states that it has to be done once in a year, it has to be done once in a year. Otherwise, you are responsible for not doing it. So within the law, whatever is permitted can be done based on these methods. Then calibration of flow meters is slightly different from calibration of other instruments, because in this case you are trying to measure something which is moving. So when the moving fluid passes through the flow meter and verification system, it has to be measured. It has to be measured at say like you can say once in say, yeah, at every flow rate you check 2 readings, or at every flow rate you check 5 readings. That depends on your calibration method and calibration requirement. There are many methods. Prover calibration is there, master meter calibration is there, laboratory proving is there. Laboratory proving itself, you can do it volumetric, you can do gravimetric. Sir, can I take 5 minutes off?
Please, sir, please, you can continue. No problem. We will wait for 5 minutes, sir. No problem. In the meantime, there are some questions. I will take these questions as per there's a few of them have asked about the legal metrology requirements.
Okay, sir. Thank you.
Please, sir, please. Dikshit sir is there. Very good. Sir, Dikshit sir, you are here?
Yes.
Very good. Sir, there are some questions I am just reading out. We will try to reply. Can legal metrology verify and stamp flow meter used for measures liquids other than liquid petroleum projects? Yes. Basically, the legal metrology does not restrict itself for a particular commodity or for a particular liquid. It is for all type of measurements taking place in transaction or in production. So we can verify and stamp wherever the flow meters are used, even if they are used in they are not used in any transaction or production. The user can get it verified and stamped if required. Am I right, sir?
Yes.
But I think, as Professor Suresh has just explained, it is very much required that the weighing and measuring instruments or any type of equipment which we are using, unfortunately, the most important or the biggest problem maybe with the medical equipments, which are either calibrated or not calibrated, we are not aware of that, needs to be calibrated, must be calibrated. All type of equipments needs calibration after a regular period of time, because we are all aware, due to tear and wear, accuracy or the calibration accuracy, I should say, lost with the passes of time or with its users. So it is always advised, recommended to get your weighing and measuring instruments verified and stamped or calibrated at a regular interval of time.
Yes.
The second question is, as per legal metrology, any tolerance are allowed? Yes, it is very important. If we talk about these flow meters are basically, for these flow meters, we are having a separate category or separate recommendation as per International Organization of Legal Metrology, OIML recommendation. It is R117, which speaks about measuring systems for liquids, other than water. And this covers all type of flow meters, tank loading, shipping loading, or any type of tankers which are moving, dispensing unit. So all LPG and all type of basically flow measurement systems are covered under 117, apart from gas meters, which has 137 separate recommendation, and the CNG dispensers, which also has a separate recommendation. As far as the accuracy or the tolerance is concerned, these flow meters or the measuring system are having the accuracy from 0.3, 0.5, accuracy class 1 and 1.5. Similarly, the tolerances allowed are for an accuracy class of 0.3, it is 0.3%. For an accuracy, for an equipment of accuracy 0.5. All the dispensing units, petrol and diesel dispensing units are covered under this accuracy class of 0.5 and their accuracy is 0.5%. So for a delivery of 5 liter from a petrol or diesel dispensing unit, the accuracy will become 0.5% and for 5 liter it becomes 25 ml. So this is the way we have already distributed. All the state governments have their calibration equipments, and at all petrol and the diesel stations you will find there is a conical measure of 5 liter available over there, and any of the customer, any of the consumer, if he has a doubt that the quantity is less, he can get cross-verified at these retail outlets or the petrol pump. It is actually, as per the law, it is allowed. This is now over to you again, sir. Please.
Yes, sir. Thank you.
Thank you, sir.
So the calibration of the flow meters can be done by different methods. One is prover. Prover is online provers are there, in which a ball prover, different kinds of provers are there which can be used. That is, in prover, what they do is the fluid which is passing through the meter is passed through a pipeline, basically a pipe in which the volume of the pipe section is known, and from a section what is indicated by the prover is compared with what is indicated by the meter. Master meter is a meter which is assembled, which is calibrated against a known system, is assembled in series against the meter under calibration, and these two readings are compared. And laboratory proving, the meter is taken to the laboratory, and what is passed through the meter is collected is either in a volumetric tank or in a gravimetric tank. Gravimetric means the mass of the fluid is measured. Volumetric tank or gravimetric tank, and then compared with the flow meter indication. Like the flow meter indicates like in 100 meter cube, and the actual volume is 99.5 meter cube as per the volumetric tank. Then the inaccuracy is 0.5%. For gravimetric, also the same system is used. Only difference is the mass of the fluid which is passing through the meter is collected in a tank which is kept on a weighing machine, and the mass of the fluid is measured for a known time interval, and then the mass of the fluid which is passed through the meter during the same period is compared with the mass of the fluid with the I will show you the gravimetric method and volumetric method as available in FCRA. I have a short film on that. I'll show you that. And we have a dynamic term called dynamic traceability. It is not static traceability only makes, suppose in a gravimetric system of flow meter calibration, you make the measurement of the mass of the fluid collected, the time for which the mass is collected, and the density of the fluid which is being collected. So you have three measurements there. One is mass, one is time, one is density. This flow meter calibration is an integration of all these things. Like volume is calculated from my mass by density, and then volume by time will give you the flow rate. The flow rate at which it shows so much accuracy is the calibration, or inaccuracy is the calibration. So we say that all these things is an integrated system. It is a concoction of these standards which gives you the accuracy or inaccuracy. So this has to be compared with the similar system elsewhere in the world. Like say flow meter which is calibrated at RRSL, for example, is taken to FCRA and then calibrated FCRA again, and whether you get the same kind of accuracy for both these systems is compared. That is called national dynamic traceability. And if you want it internationally dynamic traceability, then a flow meter which is done at this system is taken to a system which is equally good, like say PTB Germany, or at FCRA we used to take it to NEL UK, or PTB Germany, or Delft Hydraulics, or Danish Technology Institute, or you can say Denmark standards of Dutch standards. Everywhere similar systems are available, and you take a meter which is calibrated here, take a meter which is calibrated calibrated there, and compare the results between these two, which is mandatory for getting the NABL accreditation nowadays. So NABL and accreditation standards mandates for this kind of comparison, international intercomparison or national intercomparison for obtaining traceability. For obtaining the NABL accreditation, which ensures dynamic traceability. It's not only for this is applicable for any kind of measurement, not only flow measurement. All flow measurements need to have a dynamic traceability because the system can affect the accuracy in many ways. Maybe due to human error, maybe due to the instrument error, maybe due to a combination of instrument and human error, maybe the system under which it is being operated, like something like which is to be operated at 20 degrees centigrade. You are not maintaining 20 degrees, you are maintaining 25 degrees, then there can be an error. So these kind of things will come out during the dynamic traceability. Dynamic traceability ensures that your system is at par with international level systems. So which is mandatory, mandatory primarily for your confidence, not only for the law. So dynamic traceability is that. So you have static traceability as well as dynamic traceability for the calibration systems. Flow meter is developed, which is essentially, see, flow metering needs in production, processing, distribution, all these things, flow metering is involved. A reliable and accurate flow measurement needs sound engineering practices, a selection of measuring equipments, installation and maintenance, interpretation and application of results. Like selection of measuring equipments, I'll tell you an example. Like if you have a pipeline which is coming from top, say by 3 meters, it comes down and then it turns a sharp turn at the bottom of the 3 meters. It takes a sharp turn. Immediately after the turn, you place a flow meter, turbine flow meter, and try to measure the flow. You will not get the flow accurately. So there comes the term upstream, downstream, straight lengths. Straight lengths, they call it straight lengths. So straight lengths, see, as we have discussed, the flow can be measured properly if the fluid and the flow is treated properly. If the fluid and the flow is not proper, then you're not going to get an accurate flow measurement. Therefore, the method is, if you have, say, for example, multi-phase flow, so some air is getting into your liquid, then you have air removers in the flow line, which will remove the air and then send it to the flow meter for measurement. You attach to certain flow meter. Say, for example, positive displacement flow meters, you have air removers at the upstream of the meter, which removes the air and then send it to the positive displacement meter. So turbine flow meter, if you say, they would say turbine and the DP meters, they would say 20D upstream, 10D downstream. What is this 20D? 20D is 20 diameter of the pipeline. And 10D is 10 diameter of the pipeline. 20D, 10D, the standard says 20D, 10D, you apply 20D, 10D. But you have a condition, you have to see your condition also. So if you have a zigzag pipeline upstream of the flow meter and then you give only 20D, it may not be sufficient. So your idea is to give a steady flow with a proper velocity into the flow meter so that the flow meter can accurately measure it. You give a flow which is pulsating, you give a flow which is swirling, you give a flow with multiple phases, with the air coming in between, then you cannot blame the flow meter for not measuring it properly. The flow meter can measure it properly only if you give a proper fluid flow into the flow meter. Then only it can perform to its what do you say, specified accuracies. Otherwise, you just cannot blame the flow meter for measuring. So selection of the measuring equipment. Selection of the measuring equipment, when I say selection for the required accuracy, as we discussed earlier, for a 2% accuracy, you don't go for a mass flow meter. For a 3% accuracy, you don't go for a mass flow meter. For 0.5% accuracy, maybe a turbine flow meter is sufficient. 0.2% accuracy, you may select a flow meter which is mass flow meter, or maybe modern ultrasonic flow meters, or these kind of things. That again depends on your maybe the law mandates for such kind of things. As Agarwal sir earlier rightly pointed out, in as per OIML, certain class of standards, certain classes of meters needs certain kinds of accuracies. So if that particular measurement needs that particular accuracy, then you cannot go for an instrument which is inferior to that, because the law mandates that you have to have such kind of accuracies. So selection of measuring equipment for your requirement is very important. Then installation and maintenance. See, it is not like Hero Honda. You put a meter and then forget it. It's not like that. You have to maintain it properly. You have to install it properly. You have to give proper flow to it. You have to, in between, intermittent checks are required for the flow meter to ensure that it is performing properly. So installation of the meter is important. Maintenance of the meter is important. Properly selecting a flow meter is important. Properly placing a flow meter at the right place is important. All these things are important. You cannot just say that if I buy a flow meter, so I make the flow measurement accurately. That statement itself is totally wrong. You have to properly select the flow meter, properly place it at a place where the flow measurement can be taken place. If the flow is not proper, put some upstream, downstream lengths, or you can put some flow straighteners, as you call flow. You can straighten things out. No, if the flow is not straight, then you can straighten it out. Upstream flow straighteners at the cost of flow straighteners are always costly, because flow straighteners consumes money. How? Because flow straighteners, you lose the pressure, pressure of the fluid. The pressure is generated by the pump. The pressure, so the pump has to be selected in such a way that it will accommodate the pressure loss also. So the pump cost goes high, pump running cost goes high. So you can. So all these things are a combination. You cannot, you can say, these are mutually relative. So mutually dependent, not independent. So what accuracy is required, whether you need to go in for upstream length is not there. So that is important. Installation and maintenance of the flow meter is important. You can, in the modern flow meters has maintenance checks are there. So you can check the flow meter through its software, or maybe a technician can tell you from the sound itself, he will tell you that the flow meter is not working properly at a particular flow. Because see there are these equipments, the planned equipments and the flow meters has a signature curve. When it is properly measuring, the sound itself gets registered into your head, and the slightest of difference in the sound itself will tell you that there is some problem with the flow meter or the flow. So certain, I have seen certain applications where you have designed a particular applied a mass flow meter for a particular place, and then you have increased the flow. Increase the flow means increase the pressure loss. Increase the pressure loss means probability of two-phase flow inside the flow meter, and cavitation. Resulting cavitation can result in your inaccuracy of the flow. So basically two phases inside the flow meter, which will result in the cavitation, probably damage of the flow meter in the long run. All these things can happen. So therefore, installation, maintenance, then interpretation and application of the results is also important. So certain people interpret the results in a not in a proper way. I won't quote it, but interpretation is very important. And what is the result which you are getting from the flow meter? What is the accuracy you need, whether you are getting within that, whether the inaccuracy or the accuracy of the flow meter is within the bandwidth of your requirement. All these things is part of interpretation and the application of the results. A flow meter shows a bad reading on fine morning, and you suddenly don't change the flow meter or repair the flow meter. It may be due to some errors which has happened unknowingly, or due to some foreign content passing through it or something like that. So application of the results, interpretation of the results is also important. That needs experience. You from there is no better person than the people who are working in the plant, who can interpret the results and apply the results for a better accuracy. Measuring the flow of liquids is very critical. It can make the difference between making a profit or taking a loss, as is obvious. Inaccurate flow measurements or failure to take measurements can cause serious results. So that can be even disastrous results, I would say. So a pressure measurement, a wrong measurement can lead to disastrous results. See, that is, say, even a temperature measurement in a blast furnace, how it affects your blast furnace, you can imagine the entire furnace will go waste if your temperature measurement is not proper. So similarly, the flow measurement also, there are cases where which can lead to very bad results or even disastrous results if you are not making it properly. Basically, the flow rate is determined inferentially by measuring a liquid's velocity or change in kinetic energy. Q is V into A. V is the velocity, A is the area. A is basically, you would say, is a constant. So basically, you are measuring velocity. In most of the flow meters, you are measuring, except some flow meters, you are measuring velocity directly or measuring velocity as an indication of something. That's what's happening. So any change in velocity measurement can affect your flow rate measurement. Area is constant, so only variable is V. So volumetric flow rate is volume is area into length or volume into area into velocity. Area is, say, meter square, velocity is meter per second, so your flow rate is meter cube per second. So that's what is happening. The fluid flow rate measurements are established differently from counterparts in length. So identity standard. So when you say flow rate, the flow rate is meter cube per hour. How do you maintain an identity standard of meter cube per hour? You can maintain identity standard of meter cube. You can maintain identity standard of hour. But meter cube per hour together does not exist. So meter cube per hour is called derived standards. So you measure meter cube separately, you measure hours separately, and find out the flow rate from meter cube per hour. So they do not exist at identity standards. It's facsimile or equivalence must be concocted. That is, you have to fabricate it and then use it to quantify the systematic errors that might exist between or among measuring in facilities in fluid flow rate. That is what that is what makes flow measurement unique from other measurements. So there is no identity standard as such which exists. So therefore, the complication associated with flow rate measurement is also more. So the probability of you making a mistake is also more. So that is the difference between the flow rate measurement and other standards. The flow in a pipe ideally is you always have a velocity from the wall to the center. It's same velocity you are measuring. No, it's not. The real world, the velocity is a curve. It's velocity profile. If you measure velocities at various depths in a pipeline, it will be different. That is called velocity profile, which is normal, which is not abnormal. So this is some terminologies I am just referring. This Reynolds number, which is regularly used for calculating or identifying or characterizing the flow. A single dimensional parameter which formed as the ratio of the inertial to viscous forces. The magnitude is indicated by rho Vd by nu, fluid viscosity. So that is Reynolds number. Reynolds number is liquid's viscosity in centipoise. So this is the indication which you normally get. So these terms which you generally encounter with Reynolds number, or you can say uncertainty, then accuracy, all these things, repeatability, all these things you encounter when you're dealing with the flow meter. Laminar flow, turbulent flow. What is laminar and turbulent flow? Laminar flow, turbulent flow are the types of normally encountered indicators. The Reynolds number is less than 3000. It is called laminar flow. 2000. 2000 and 3000 it is called a transition flow, and above 3000 it is called turbulent flow. Turbulent flow is the one which you normally measure. It's not the laminar flow or the transition region. That is, if you remember, it is rho Vd by nu. If V is more, then obviously Reynolds number is more. So rho is more, Reynolds number is more. If rho is less, so you take the case of a liquid and a gas. Liquid rho is more. Say for example, water 1000 kilogram per meter cube, but air, you take the case of air, it will be say 1.2 kilogram per meter cube. So Reynolds number will be low in those cases. So therefore, the velocity will be very high in case of air flows. You are trying to measure something when it is in turbulent region. I hope I am clear. So these are all basic physics which you have already probably undergone in school level. This then the flow meter performance is also affected by the density. It's affected by the viscosity. It is affected by, can get affected by pressure, temperature, velocity. See, viscosity, you take the case of viscosity. If you take the case of a positive displacement flow meter, if the viscosity, you will see that when the viscosity is very low, the probability of error is more. When the viscosity is higher, probability of error is less. It is an inherent characteristic of the positive displacement meter, because positive displacement meter is something meter which you can say it would take out a certain volume from the flow intermittently and put it back to the flow. So there is a gap between the rotating element and the casing. The leak between the rotating element and the casing decides the error of the meter. So the leak can increase if your viscosity is low. The leak will decrease if the viscosity is less, because if the viscosity is more, the liquid which is sticking to the thickness of the liquid which is sticking to the wall of the stator will be more. So therefore, the gap between the stator and the liquid, I mean rotor, will be less. So there is a viscosity effect is there, density effect is there, pressure effect is there, temperature effect is there, velocity effect is there. So these are the certain things. When you are specifying a flow meter, the flow meter, you can buy a proper flow meter only if you divulge the proper information or under which you have to make the measurement. What is the temperature at which you are going to make the measurement? What is the pressure at which you are going to make the measurement? What is the viscosity range in which it will come? What is the velocity generally, or what is the flow rate you would say? And what is the pressure under which you are making the measurement? So you can make a proper measurement, proper flow measurement, if you select the flow meter properly, if you install the flow meter properly, if you maintain the flow meter properly, if you calibrate the flow meter properly, and if you specify the conditions under which the flow meter is operated is also properly. That is, the process media has to be given, density has to be. You cannot use a gas flow meter in a liquid application. You cannot use similarly, you cannot use a liquid application flow meter in a gas measuring instrument. So these things have to be specified properly. What is the density range which you will encounter? What is the viscosity range? You cannot say a particular density, but you can always say that, say for example, if you're measuring crude, the crude will come, say from 13 centistokes to 100 centistokes is the crude viscosity which might be happening. So the density, the viscosity, the pressure, temperature, because temperature can affect your viscosity also. Even the temperature increases, your viscosity decreases for liquids and increases for gases. So these things can affect your measurement. Therefore, when you tell the flow meter manufacturer will give you he is the best person to select a flow meter from his range of products and give it for your application. It's not you who can select a particular. Okay, of course, you have a history of particular flow meter which is properly performing in a particular application, then you can buy the same flow meter. But if you're going in for a new application, then you give all the information which is required, or which the flow meter will encounter in the application to the person who is supplying it. He will select a proper flow meter for you, for your application, for your fluid, and then give it to you. It is not the initial cost itself which has to be considered. The cost is one thing. You have to consider whether it works properly works properly and reliably for a long duration of time under the conditions of operation. This is also important, because say a temperature encounter, suppose you have a temperature, you have specified a temperature of 50 degrees centigrade or 60 degrees centigrade. Unfortunately, the process temperature goes up to 80 degrees centigrade, and you would say suddenly the flow meter goes out of order. That kind of reliability. We need little more reliability, little more safety factors for the flow meter selection. Then another term which is very frequently misused or misused is you can say percentage full scale. 100 GPM, if it is, suppose the present value of accuracy, I'll show you the example. The percentage accuracy value is constant and applied to actual flow rate. Suppose if the flow meter is 1% accurate, at 100 GPM, the error will be 1 GPM. At 50 GPM, the error will be 0.5 GPM. That is 1% accurate. That is absolute 1%. 10% GPM, it will be 0.01 GPM. But that is in absolute value. If you're stating it as percentage full scale, then 100 GPM, they would say 100%, 100 GPM, 1% of full scale. The specification of the flow meter is stated as 1% of full scale. That is 100 GPM, it will give 1% error. At 50 GPM, it is again the 1 GPM error, which is 2%. At 10 GPM, it is again giving 1 GPM, which is 10% error. So full scale can be, it's something like a misguiding term, full scale, percentage full scale. So that we have to be careful while selecting the flow meter. Generally, I think reliable people don't go in for such kind of misleading terms. Percentage rate and percentage full scale is a thing which has to be taken care of. I have given a general introduction to flow metering and its you can say intricacies involved, the calibration intricacies involved. Now I will try to cover certain certain important flow meters which are used for flow measurement, like differential pressure, positive displacement, some velocity meters, some mass flow meters, and it's the differential pressure flow meters, the pressure drop across the flow meter is proportional to the square root of the flow rate. That is, basically the differential pressure, you can say orifice plate is nothing but a plate with a hole. You have a plate with a hole. You make a hole in a plate, put it in the place, and you make the differential measure the differential pressure across the plate. You will get the indication of the flow rate. So very simple. So the flow rate is obtained by measuring the pressure differential and extracting the square root, which is directly proportional. Primary element causes a change in kinetic energy. Here the basic principle is the primary element causes a change in kinetic energy, which creates a differential pressure. The differential pressure is induced in the flow by inserting a flow meter into the stream. The secondary element measures the differential pressure across the flow rate, which is a square root is proportional to the flow rate or velocity rather. So this is the thing. I hope you can see. This is flow measuring principles of the differential. So you have an orifice. Direct as a vena contracta is also there. At vena contracta, you measure the pressure. So the pressure upstream is measured. Then the differential pressure gives you an indication. Different kinds of not necessarily it's concentric orifice, eccentric orifice is there, segmental orifice is there, different kinds of orifices are there. Then you have ventures, you have nozzles. uh, this these are different kinds of DP measurement, that is differential pressure measuring instruments. Orifices are the most popular liquid flow meters. That is, I think even now, more than 60% of the flow meters available worldwide is DP flow meters. Most orifices are concentric, eccentric, conical type. Then venturi tubes. It can handle flow volumes at low pressure drops. I think you understand that venturi has a gradually decreasing volume, gradually decreasing area. Therefore, the pressure drop across the venturi will be less than the pressure drop across the orifice. So the operating cost will be less, but the cost of the venturi tube can be more. So you will decide which one you need. These are used for both liquid, gas, and steam applications, suitable for extreme temperatures and pressures. There is no moving parts, low initial cost, but rangeability 30%. That is, you can say accurate measurement you will get from. So if you are selecting for up to 100 meter cube per hour, 100 to 30. That is limited rangeability. 30 to 100 will be the rangeability affected by changes in density, pressure, and viscosity. Maintenance will be intensive. These are the disadvantages. And I will show you a video, I think, which will give you a. Hope it is working. Yeah. So I think you have understood the difference between orifice, plate, ventures, and nozzles, and why it is being used, gradual reduction of area and all those things. But of course, the cost of the equipment will depend on which one you select. Orifice is least cost. Uh, of course, venturi and nozzle will be costlier because it also depends on the profile which you develop in the venturi, profile which you generate in the nozzle for lesser pressure loss will cost you more. Okay, I won't go into the details of those things. But again, I hope you understood the difference between venturi, orifice, and nozzle. Uh, Now, there is another instrument called pitot tube. Pitot tube sends two pressures simultaneously. There is a total and a static pressure. Basically, the pressure with the velocity, that is the total pressure, and the pressure after the velocity downstream is also measured, which is an indication of, again, velocity. The impact unit consists of a tube with one end bent at right angles towards the flow direction. Again, I will show you a video which will give you a better idea.
Sir, it will be very nice if you kindly speak at the same time what you want to show.
Pitot tube. Okay, pitot tube. You can see they are speaking. There is a commentary. I will overlap that. I mean, I don't know. I will try, sir.
We are not able to hear anything when during this video.
Acha, video. One second.
We could not have anything.
You are not hearing anything.
Yes, sir.
Oh, good. I thought you were hearing. One second.
I'm sorry. We are not hearing. And sir, when you will share your presentation, kindly share the videos also, so that when I will.
I will share. I will share. I don't know why it is. I am hearing that, but
No issue, sir. We will please continue. We will share this presentation as with the videos with the participants.
okay, okay. So this is pitot tube. You can see the pitot tube. Pitot tube, I'll give the commentary. Pitot tube, it's a bent tube. The bent end is, you can see that there are holes upstream and downstream. The upstream holes indicate the total pressure. So these holes will ensure a representative pressure of the upstream. You can also use a pitot tube which is rotated to 90 degrees, two pitot tubes at the same time. So that is upstream will give you the dynamic pressure and downstream will give you the static pressure, which gives you the pressure differential. So the differential pressure is a direct measure of the flow velocity. So this can be used for liquids as well as gas. This can also be used in the application of saturated steam, gas. Now, there is another meter called the vortex flow meter. Vortex flow meter is based on the vortex meters make use of natural phenomenon that occurs when a liquid flows around a bluff object. Eddies or vortices are shed alternately downstream of the object. So the frequency of vortex shedding is directly proportional to the velocity of the liquid flowing through the meter. That is the basic principle. That is, a bluff body is placed in a flow, and you will say, I can say, the flags fluttering. You would have seen the flags fluttering. Flags are fluttering because the flag post works as a bluff body, and the downstream vortices makes the flag to flutter this way or that way due to the vortice pressure drop. The frequency of the vortices generated or the fluttering will be proportional to the velocity. If the velocity of the air is high, then you would see that the vortices are formed at a more frequent rate than the low velocity. The frequency of the vortex shedding is directly proportional to the velocity of the liquid flowing through the meter. This is what vortex meter. There is a bluff body. As if you see that vortices are being shed at the downstream of the meter. Again, I'll show you. I am not. I don't know why the voice is not coming. I am hearing the voice, but you are not hearing the voice of the video. Uh, Anybody can correct it, then it will be
I
better.
think, Atulji, can we do something from here?
Hello?
Or you
Can
can
we do
direct
something
me
from
to
here?
do whatever is to be done, I can do.
We are not able to hear the voice.
Voice of the video.
Yeah, voice of the video. Anyway, sir, you please continue.
Okay.
వీడి బాజీ వేడి వస్తుందా చేస్తున్నారా ఎర్ర
All other participants are requested to kindly switch off their mics.
So you can see that the vortices are being formed by the bluff body when the flow takes place. you can see the number of vortices formed will be more when the velocity is more. And it measures the frequency. So that is, in certain cases, the vortices cannot be formed because the velocity is low. In that case, you can go in for a lower diameter vortex meter, which will generate the required vortices. Saturated steam it is applied, gases it is applied. So vortex meter is a popular meter in saturated steam and gas application. Now, this is a rotameter, which is very commonly used meter and not very accurate. This just gives an indication of flow rate. This is differential pressure, but accuracy is not as good as one would like to have. Then positive displacement flow meters. Operation of these units consists of separating liquids into accurately measured increments and moving on. Each segment is counted by the flow meter will segregate a particular amount of fluid within its chamber and then release it to the downstream. Collect it from the upstream, collect it in the chamber, release it to the downstream. The number of rotations of these chambers will give you the accurate volume of what is total volume. Each segment is counted by connecting into a register, which is a very common meter which is used in petrol bunks, oil, ATF transfer, and all those things. Positive displacement are used. I think most of the legal metrology officers would have encountered this flow meter many times. So there are different kinds of PD meters available. One is I won't go into the details because the time does not permit that. Then another thing is electromagnetic flow meter, which is commonly used based on Faraday's laws of principle. That is, the liquid serves as the conductor and the magnetic field is created by energized coils outside the flow tube. The amount of voltage produced is directly proportional to the flow rate. Flow rate means the velocity. As the velocity increases, magnetic field, energized coils, it creates more voltage. This is the theory of operation. Magnetic coil is basically Faraday's law. The advantage is that there are no moving parts in that. It creates no pressure loss, very wide rangeability. Obstruction is not there. Ideal for slurries. It is easy for maintenance. Disadvantage is liquid must be conductive. If the liquid is not conductive, the conductor has to pass through the meter to measure it. So the liquid is not conductive, then it will not measure. Let's say, for example, DM water, which is not conductive, demineralized water, so it will not measure. You have to add some salt into it or something like that to make it conductive. Then only it will measure. The physical pressure and temperature limits is also there for magnetic flow meters. I'll show you the video. It's unfortunate that the audio is not coming. I'll share the presentation in any case through mail. Agarwal sir, I'm sure he will pass it on to you. Anyway, I will show you the video, which will give you a reasonable indication of what is happening inside the flow meter. The coils generate a constant magnetic field. There are two electrodes in it. You can see that there are two electrodes here, which is fixed to the wall of the tube. Then if there is no flow, there is no voltage induced. And as the conductor moves across the electrodes, the electrical voltage is generated, which is measured and which is proportional to the velocity of flow. As the velocity increases, the voltage also increases. This is a technical method to eliminate interference voltage, which can affect the accuracy of the flow meter by changing polarity of the electrodes in between. That is not the basic working principle. It is an added advantage which will avoid interference voltages and improve the accuracy of the flow meter. This is one of the very common meters which are used in water industry. Another thing is the mass flow meter, the continuing need for more accurate flow measurement of mass-related processes, chemical reactions has resulted in the development of mass flow meters, which is the indication from the meter. The difference between other meters is generally they measure the velocity or indication of velocity, which is again used to calculate the volume flow rate. Here you get a direct mass indication from the meter. It's called Coriolis mass flow meter. Coriolis effect is utilized in this meter. Basically, if you would have experienced that if you are walking across or walking radially in a rotating platform, like when your children are playing in a park in a rotating platform, and you walk across the rotating platform radially, you will experience two kind of forces. One is the force created by the centrifugal force because of the rotation. Another is you are changing your position continuously across the radius. A moving particle across the radius continuously in a rotating platform will create another force called Coriolis force. So this is basically measured and proportional to your movement velocity. So that is what is being utilized in this flow meter. Basically, the Coriolis force or Coriolis correction is done even in rockets for Coriolis force. So the air which is moving from say South Pole to North Pole is moving across radially, and when the Earth is rotating, therefore it also experiences a Coriolis force which will make the directional change in air. The same principle is made use of in this flow meter. It's Coriolis flow meter. So again, the commentary is not there. I'll try to explain in the background. So So this is the inside. Something similar to this is the inside of a mass flow meter, single tube mass flow meter, in which there is no flow taking place at now. So the tube is made to oscillate using some technology, some electromagnetic force. It is being made to oscillate. In an oscillating tube, when the flow takes place, the tube experiences Coriolis force. You say the tube is experiencing the Coriolis force. See how the tube moves. This is an exaggerated view, of course. Now the flow tube experiences Coriolis force. So the oscillation of the tube is directly proportional to the mass flow rate through the tube. These flow meters can be used for both for liquids and gases, and which will give you total flow, which will give you an indication of density. Therefore, you can calculate the volume flow The frequency gives an indication of the density of the fluid contained in the tube. So those are some of the flow meters which are generally available in the market, and now calibration standards, fluid flow visual specific transfer standards. In this, I'd say. A calibration standard generally needs a source of flow. It's generally a pump. It may be a blower, or maybe a constant head tank with appropriate auxiliary equipments. A test section into which the meter and its adjacent piping can be installed for providing the flow or duplicate the conditions of the flow which is expected in the operating conditions. A flow determination system having a specified level of performance and appropriate proof to specify that assure the performance. So these are some of the laboratories in which utilizes the gravimetric system in a fluid control research institute. I'll try to show you the water flow lab video. Fortunately, the commentary which is given in the side. It is written on the side. So you can see the flow rate which is taking place through the diverter system. Then we have a large water flow lab in FCRI, which uses master meter calibration method for calibration of flow meters. The uncertainty is less, as you can see, it's 0.5%. But you can go up to 3000 meter cube, 3000 mm diameter, and flow rate up to 15,000 meter cube per hour. These are some of the facilities at FCRA. I think it's time for me to conclude. We have discussed fluid flow measurement and the related terms, flow and the related terms, and theory and metrology and importance of flow measurement. Then some different kinds of flow meters. I would say some overview of some different kinds of flow meters. Then calibration of flow meters. It was unfortunate that I could not, the video was not having audio coming out of the video. I'm sorry for that. Maybe I can share the entire presentation to Agarwal Saab. He will share it to the audience. Thank you for your patient listening.
Thank you. Thank you very much, sir. It was a nice and wonderful presentation. I say it is unfortunate that we cannot heard the voice of the videos. Otherwise, it could be I tell you, this was one of the best presentation which we have so far since last morning.
Thank you for the nice words, sir. I mean, thank you.
Thank you. I'd like to thank all the participants, specifically, sir. Now I'd like to request Mr. Atul, kindly take the photographs of all. Remove this presentation from the slide. Sir, we will take 1 more minute. We will take the pictures of all the participants and put it on our all portals, this Twitter and Instagram, Facebook, etc. And your presentation will be shared with this video to all the participants through Facebook as well as through the YouTube channel. With presentation as well as video presentation, I would like to request, sir, kindly share me the videos also, so that when we
Sure, I'll send it separately to you through mail. Your mail ID is same, sir. I mean,
same.
Okay.
Same. Otherwise, I will again share it to you, sir.
Please, sir. I'll send it to you.
Atulji?
Sir, I request you please unshare the PPT so we can take a few snapshots.
Yeah, sure.
I'm sorry, I will take the questions. We have received the questions. Sir, I will share these questions to you because time is short. I would not like to extend it. I'm
Okay,
sorry,
sir.
I have another meeting at 1 o'clock.
Okay, sir, please.
It is all legal metrology. Use YouTube and all are the legal metrology. Again, we will share these links of these portals, all the portals in our this mail, as well as when you're getting the certificates, all the links are given over the certificate itself. All the channels are mentioned on the certificate. Even we will share it in the group, WhatsApp group, as well as in mail. So kindly unshare the presentation. Atulji, can we take the pictures?
No, sir, because PPT are shared in shared mode, so we can't.
Can you remove it from your side?
No, sir, it's not right. Sir, from the sir side, he can also remove. Yes, sir. Yes.
Thank you very much, sir. Thank you.
Okay, I think now it's okay, na?
Very good, sir. It is very good.
Okay.
Anybody who would like to speak? I can see my good friend, Mr. Bhaskar. Namaste, sir. Raju.
Hello, sir.
Hello, how are you?
Fine, sir. Fine, sir. Very nice one, sir. It's Suresh, sir. We had interacted with him in FCRI, sir. Sir, I am asking about any malpractices associated with this flow meters. We have encountered in some other northern states. In one refinery, K factor was changed in flow meter. So that
Can you repeat what you're saying, sir? Can you repeat what you're saying?
Sir, by changing the K factor of the flow meter,
Okay.
can we do alterations?
You
How
have
can we
changed
control?
the ceiling is there. The ceiling is there. No, you can control the access.
Yes, sir.
You can control the access.
Okay, sir. Okay, sir. Can you give any predictions other than the ceiling, sir? Other than the ceiling.
Other than the ceiling, there must be a history of a change of K factors in the memory of the flow meter. If it is there, then you can check
Okay,
it
sir.
during inspection. There will be a history. If they change the K factor, it will get registered in their memory. So you can check that. You can ask them to show the history of the previous year. That is, you do a ceiling, and within next ceiling, if they are changing anything, they have to get the authorization from you. Without your authorization, they are not supposed to change anything. Be it K factor, be it any other parameter. For breaking the seal or accessing the equipment, or there can be a password, or for password changing, there can be even a paper seal. I think in some of the instruments, you put a paper seal also for access control.
Thank you, sir. Thank you.
Okay, sir.
Dr. Sinha is also there. Sinha sir, namaskar. I would like to thank all the participants.
Thank you.
Thank you very much, sir. Thank you. Thanks a lot, sir.
Thank you. Bye.
Thank you, sir. Thank you, Suresh, sir.
Thank you, sir.
Thank you for your attention. Hope to see you soon.
Thank you, sir.
Thank you, sir.
Okay, bye. I'll send the presentation to